Yeah, I think just...
Yeah. And once we're ready to go live, you just let me know.
Okay. I'll let you know.
Okay.
All right. Whenever you are ready, you can get going.
Okay. So hi everybody. My name's Dana Humphrey. I'm Dean of Engineering at the University of Maine. Everybody just calls me Dana. Thank you for joining us for one of our bi-weekly virtual tours of the College of Engineering. We have 11 different engineering and engineering technology majors here at the University of Maine. We're what I call a medium-sized engineering program. We're big enough such that you have a lot of choice, but we're small enough such that most of your faculty, you'll know your faculty by first name basis. So we're really that right size. We've got a lot of incredible lab facilities here for our students to work in. Today, what we're going to go in is the Advanced Structures and Composite Center. This is a lab that has 100 undergraduates who work here. It's a 100,000 square foot facility with about $100 million worth of capital equipment in it. You're really going to be impressed by the things that we have in this lab. Second part of the tour, we're going to go to the actual construction site for the Furlan Engineering Education and Design Center. We are holding these tours every other week. Every week we're taking a different tour route. So tune in again 2 weeks from today and we'll have another tour for you. So I'm going to take and put on my hard hat and my safety glasses and get ready to go into the lab here. So if you'd walk this way, follow me into the lab. Okay, so we've got us buzzed into the lab. So that was just the first step to get into this lab. So now it's the second step to get into the lab. Before anybody gets to work in a lab like this, you've got to have safety training. That's why, and I've had base level safety training to be in this lab. That's where I've got on my hard hat, safety glasses. So we're ready to go. So we've got one more set of key doors to get through. Then we'll actually be in the lab and we're going to meet up with one of our students. So follow me. All right, 3 doors, locked doors, now we're in. So I'd like to introduce everybody to Ben. Ben is a senior in our mechanical engineering program. Come on over here, Ben. Ben's a senior in our mechanical engineering program. He's working in this lab, and maybe Ben, explain a little bit about yourself, where you're from, how it came that you're a student here at the University of Maine, and then what you're working on in the lab. And I'm going to step back for a moment or two.
Yeah, so as Dean Humphrey mentioned, I'm a senior in mechanical engineering. I'm from Saco, Maine. I kind of grew up, I was always enjoying my math and science classes. I took an engineering class in high school, and eventually I came to the conclusion that UMaine, especially looking at this Composite Center, is a really great place for me to study engineering. And so far, 4 years in, I'm very happy with my decision. Here at the center, I'm working on a project with some Maine boat building companies to study the feasibility of using 3D printed materials in their boats. So some of the things we're doing are freeze-thaw cycling to see how the 3D printed material can handle weathering, the cold temperatures during the winter, and also some UV conditioning, so it'll study how well they can handle being in the sun for long periods of time. So after that, we'll test those and hopefully give boat builders some good results. And we're also looking at 3D printing some of their components so they can make rapid pieces and hopefully cheaper pieces as well.
Ben, what's your next step? What do you plan to do? Because you're a senior, so what's the very next step for you?
I'll be doing a 5th-year MBA program here at UMaine. They make it really easy, so I've done a couple business classes in my undergrad, and I'll take 2 graduate courses next semester. And then after 1 year, I'll graduate with my Master's in Business Administration.
So that means, Ben, you'll have 2 degrees. You'll have your bachelor's degree in mechanical engineering. You'll have an MBA. You'll be very happy to know that there was a nationwide survey that was done to determine what's the maximum, the pair of degrees that will result in the absolute maximum salary. It's Bachelor of Science in Engineering with an MBA. And so you're following right on that path there. The other thing I'd add is that the most common bachelor's degree of the executives of the Fortune 500 companies is engineering. And most of them somewhere along the way got an MBA. So you're going to be set to run like Ford Motor Company or Chrysler or whatever. So you're going to be all set.
Perfect. That's what I like to hear.
Excellent, Ben. So thank you for joining us for a few minutes today. I know you got lots of things to work on in the lab, but thank you and have a great one.
Thank you. You too.
Thank you. Okay, so follow me. We're actually going to go to the far corner of the lab and then kind of work our way back. There's lots of things happening in the lab today, so I got to be careful where we go. We do have a contractor working in here today, modifying some of our spaces. Okay, so we're still clear, so we're going to keep following me. Okay, so here we are. This is the far corner. Oh, we've got lots of interesting things to look at here. Well, nobody's here today, but let's take a... This is where we actually make composite parts. This is part of the building that's temperature controlled and humidity controlled because that affects the quality of the parts. Some of the things that you find yourself doing as an engineer is you need to determine, is what I'm doing really working? So what we have laid out on the table here is we have what are called test coupons. These were cut from some of our layups here. And what they'll do on these, they'll do tension tests on these to determine how strong they are. If we kind of take a look down the table, you can see we've got quite an array of these. You have to do enough of these such that it's statistically significant. Now, engineers are really smart people. They've got good skills to design things that are supposed to work. But at the end of the day, you still need to be able to test and verify. So no matter what engineering major you're thinking about majoring in it, keep that in mind. You're able to design and come up with some great solutions, but you need to have the ability to actually test and confirm that the solutions that we have, that you've come up with, are actually going to work. Sometimes you do this with small scale samples, but as we're going to see at different stops in the lab, sometimes we do this at very, very big scale. So we're going to walk around here just a little bit. Take that out of the way. I'm going to point out this is a portion of a wall from a shipping container. So we've all seen shipping containers, the ubiquitous boxes that are on the back of trains, go into ships, you see them on the back of trucks. We're making the walls out of composites. And these actually have sensors embedded in them such that they can detect if the walls of the container have been breached. And the reason that might be important, we don't want people to steal what's in the container. And especially for containers that are coming from outside the U.S. to inside the U.S., we don't want somebody to put something in the container that we don't want come into the U.S. This has been a very, very active project, and we'll actually see when we're out on the floor, some of the larger parts of the lab, some of the things that we're working on at actually a full-scale container. So with that, we're going to take a step back out here. We're going to kind of take a look at the setup that we have right here. This is a setup where we can start at the far end with a log and end up with oriented strand board. So oriented strand board, that's an example of oriented strand board, the kind that you could buy at the big box stores, Home Depot, Lowe's, Lumberyard, whatever. We have the ability to start with a tree and actually make oriented strand board. It means you got to take and add the glue, you got to cut into the right size pieces, you got to add the glue, then you got to take and smash it together, or squish it together. So with this line here, we're able to take and do that. Some of the other things that we have on our campus and other buildings, we can start with a log and end up with paper. One of the themes of what we do at UMaine is we try to test at full scale. Big stuff. So here we're going with a log, ending up with oriented strand board. So we're going to head out to the lab and look at the next stop here. Okay. So I don't know if any of you who are watching today like to blow things up. Well, we have the way to protect people from that. What these are blast, it's the component from a blast-resistant structure that we developed here at the University of Maine. So the outside is the blast-resistant panel. If we look just at the cross-section right here, we can see it's got plywood in the center. Then it's got two very thin layers of composites here. We look at the stud walls behind it. These are conventional 2x4s, but they're wrapped in this composite material. By doing that, it takes and changes the wood from a very brittle material, meaning that if it's subjected to a blast load, it's going to break and shatter into a lot of pieces that start flying out and could injure people. And we've turned this into this blast-resistant system. So if we can take a look at just some of this panel here, that's a conventional blast structure, no blast resistance, that we just built. It's been subject to a blast. Then we look next to it. That's a same size, but with our blast-resistant technology. There's actually a group of UMaine students who went to a site in Florida, set up these tests. We did not handle the explosives. The U.S. military did that, but this is what we did here. The purpose is for the U.S. military to give them easy to set up blast-resistant structures no matter where they're deployed. An example of a blast-resistant structure, one of our early ones, standard U.S. Army tent. So standard tent. What we have on the inside is we have these blast-resistant panels. This is a technology we developed here at the University of Maine. Standard Army tent panel with basically a wood core with a thin layer of composites on the outside, held on by these straps. These straps are actually the key to the system. Other groups are trying to take and solve this problem, and they're taking and actually bolting the panel onto the tent frame. The problem is when it got hit by a blast, and the blast is coming from the outside, it would actually cause the tent frame itself to fail. The key is using these straps that actually give a little bit out of the blast, meaning they're absorbing some of the energy, and that's got a structure that the tent stays up, protects the occupants inside, no matter where our members of the military are deployed. So very active technology that we developed here in the lab. So we're going to kind of find a way around because they are doing some construction work. So let's follow me around here. So just kind of pause here just a little bit. This is our medium-sized 3D printer. I say this is medium. We're going to get to see the really big one in a little bit. Okay. I think we're still good, so keep following me. All right. So what we have here, this is our bridge and a backpack technology we developed here at the University of Maine. And I say we, our students had a huge role in actually making this happen. What this starts out as, that's a bridge right there. It's got a fabric core in it, plastic bag on the outside, plastic liner on the inside. What we do is we blow this up and infuse it with resin using a vacuum process. And that results in a rigid tube that might look something like this. So it's rigid, it's been solidified by the composite or by the resin that we put into this. And some of the early work for this, well, one of the big questions was, in the typical application, like over my head here, this is curved. How do you take and get this into the shape of a curve with no wrinkles? Well, it's a group of 3 civil engineering students. During the summer between their first and second year, they took and figured out the weave of the fabric and that would result in the right tube with no wrinkles in it. Another group of students, again, civil engineers, once these are in place, we fill them with concrete. This is just a cutout from one that's filled with concrete. This is the problem with concrete is that when it cures, it shrinks a little bit. It shrinks away from the wall of the container. And that actually made this a lot weaker. So we had another group of civil engineering students who investigated different types of chemicals they could add that would cause the concrete to expand a little bit. In this application, those chemicals are called admixtures. And those admixtures and a group of civil engineering students figured that out. There's also an example of how civil engineers solve problems. They're big problems, they're complicated problems. What engineers do is break these big problems up into smaller problems they can solve, then put them together, then you've got a finished solution. Okay, so with that, I'm going to put this away there. We're going to move on to the next stop here. So you can see in this area here, we have a lot of test frames with different sized cylinders that we can take and use to load things. What's going on behind me, and the actual piece we're testing is proprietary, so we've got it kind of surrounded so people can't see what's in there. But we're doing a repetitive loading test. We're pulling. We're testing for what's called fatigue failure. Everyone who's watching has done a fatigue test at some point in your life, and I'm not talking about sitting in the easy chair watching the Late Late Show when you fall asleep. You've all taken a paper clip, bent it out straight, and then bent it back and forth enough times that it breaks. That's called fatigue. And depending on the engineering application, we have to be very concerned with failure and fatigue. So what we do, we're actually testing some connections under fatigue at full scale. Let's take a look at the next thing we've got here. There we go. So this is a mold for a bridge beam that's made out of composites. I think when we get further into the lab, we're going to be able to actually see one of the bridge beams. And if we can take a close-up look over around the side here, see that kind of rough texture there? This whole mold was made with a 3D printer. And we're going to take a look at our 3D printer when we get a little bit further into the lab. So with that, let's take and move on to the next spot here. So this is a water jet cutter that can take and use high pressure water to cut even through things like 6-inch steel plate. We use this in particular because we have some composite materials that are actually very hard to cut by other means. So we take and use this device to take and do that, and students get to operate devices like this with appropriate training. So now we're going from here, this is the small part of the lab. Now we're going up in the big part of the lab. So let's head out to the big part of the lab. So here we are in the big part of the lab. This whole room is 230 feet long. If we look off to the side here, that is a concrete test stand that we take and bolt wind blades to and do structural testing on wind turbine blades up to 230 feet long. I'm going to take you someplace that not very many people get to go. We're actually going to go up inside this concrete block. So follow me along, and let's head up there. So you can kind of see out back into the lab there, you can see these really huge bolts. This is what we use to actually bolt the wind turbine blade to. The block of concrete that we're standing inside, this is anchored to bedrock. Because if you think about the engineering problem, if you've got a blade sticking out 230 feet and you're pushing on it or pulling on it, it's trying to break this block of concrete out of the ground. So how do we solve that? We got to hook to bedrock. All right, so let's head down. And on the way down, we get a really good look at how big this lab really is. I always have to be careful, make sure I'm looking at where I'm going here and what the safe path is to get from one place to another. Okay, so we're just going to maneuver our way through here. This is a standard shipping container, so made out of steel, because we want to do some testing on a control, basically the normal material that are used as opposed to our new materials here. Some of the things that we do, we're actually going to do structural load testing on the shipping container. And I don't know how close a view you can get here, but that's attached to the steel. That's called a strain gauge. That measures how much the steel is either pulled or pushed as we take and apply load. Very useful technique, and one that we apply all the time here in the lab. Okay, so we're going to wander our way down a bit further. Okay. Let's see. So I'm seeing when I come in here, there's all different kind of things. So here we're getting ready to do load testing on a structure that's just an inflated structure. So when you think of structures, think about them very broadly. It's not just think of a bridge or a building. Structures come with a lot of different purposes. This is one where we're getting ready to do some testing on a structure that's just an inflated structure. Okay, now we're heading further down in the lab. Remember, this room's 230 feet long. So earlier we saw the mold that this bridge beam was made out of. So this is a bridge beam that's made out of composites. In real life, it's got concrete cast around the ends. So we're actually simulating that. If we look up toward this end here, you can see that we've already got the formwork in place to get ready to cast the concrete around this end. Then we go down to the other end. So let's head down this way to the other end. Now we've got the rebar in place, and they'll build the formwork around here and get ready to test it. The test of something like this, we'll actually take and load this to failure. We're actually going to step outside for a moment through the back door here. The important thing, the block of wood so we can get back in. Okay, here we go. Okay, that's good. All right, because this is where some of the things are that we've already tested to failure. So these are some tests that are testing concrete with steel inserts. You can see that we've actually got the crack patterns kind of mapped out here, so we can better understand how that was, how it failed. If you like breaking things, this is a great lab to work in, because you get to break real things in labs like this. This is another example of a project that we worked on. This is actually a direct relative to the project we just looked at with the composite bridge beam. This has a concrete bridge deck, very common bridge deck. Underneath it, although we can't really see too well under there, that's a composite beam. We took and loaded this to failure. One of the key students on this was Ira Hepler. She was working on this when she was a senior in civil engineering. Now she's a graduate student. You can see those things that are orange on the bottom and yellow on the top. Those are our flotation chambers from our 1/6 scale floating offshore wind platform. This had about a 60-foot tower. It was off the coast of Castine, Maine, for about 18 months. We did the testing. Now we're getting ready to test at full scale, and that's going to be a 300-foot tower, a unit that's somewhere in the vicinity of 8 to 10 megawatt unit, floating offshore wind platform. So if you're interested in renewable energy, this is a great place to work. And we just kind of look up toward the background there. You can see some of the wind turbine blades that we've tested here in the lab. So a very, very active place. We're going to go inside where it's a little bit less windy. Okay, here we go, back in the lab. All right. So the next thing we're looking at here, this is our 3D printed boat. It's got that same kind of ropey texture that we saw with the bridge mold beam that we saw a bit earlier. We can kind of see that kind of ropey texture. What's happening is the 3D printer lays this bead down at about a 45-degree angle. In this case, we start at the stern, worked our way up toward the bow. This is a 25-foot long boat. We printed it in about 70 hours. You could not go to a boat yard and get a boat that big in 70 hours. We did that here. We're the world's largest 3D printer. Okay. So now we're going to take a look at that printer. So keep following me. So this is the world's largest 3D printer. It can print 60 feet long by 20 feet wide by 10 feet tall. The print head itself is down at the far end. We can see it down there with kind of like the blue kind of cross-shaped piece there. You can also see some structures that we've been printing in the last couple of days. So it's the largest 3D printer. It's here at the University of Maine. So to take a look at what the material starts with. He's down far enough. Whoop. It's too far down for my arm to reach. It starts as these pellets here. And they basically get sucked up. And the principle of operation is that it's just like a hot melt glue gun, where it takes and heats it up enough such that it becomes a semi-solid that can be extruded into the beads that we looked at on the side of the boat. So that's a very active technology. So if you want to be involved with technology, so the next age of making things, which is going to be printing large-scale parts and structures, this is the place to come. Okay, follow me. So we're all still in the same lab. It's got lots of different parts. Okay. And let's see. I'm actually going to take a look through the window to see what they're doing and determine whether we're going to look at this part of the lab next or the place next door. We're looking here first. So what we have here is we've got a production line that makes medium-sized composite parts. I'll give an example of a part that we made. This is the conventional part. That's made out of steel. This is the differential cover off of a truck. Here's the replacement part that we printed out of composites. It starts with a blank like this. This is actually a black colored material. This is a different color, but same principle. We've got a machine that lays up a blank, a robotic arm that comes along and picks it up, and then moves it into a heating chamber. Then we actually take and press the part. To press the part, you need a mold. So this is one half of the mold. This we also made with a 3D printer that we're going to take a look at. And that's just, this is just our baby printer. This can only print 3 feet by 3 feet by 3 feet. Okay. Let's work our way down to the beginning point. We're kind of at the end point of the process now. Okay. So we're going backwards through the process from the end point up toward the beginning. So keep following me. So now we're at the starting point for the process. The first thing you need to have is a mold that has the shape of the part that you want to make. So this is a 3D printer that prints into a plastic that actually has a relatively high melting point. That's going to become important because we're actually going to take and press a hot part into that to take and make the shape that we want. So first step, we've got to have a mold. Then you need to take and actually get all the fibers oriented in the right direction. So this is a machine that will automatically lay up the fibers in the right orientation, and it gives it just little spot welds to take and kind of temporarily hold them together. It doesn't have any structural strength, but it's strong enough to keep it from falling apart. The material itself comes off of reels like this that it takes and feeds it out onto the table and at the exact right orientation. So once this is set up, this kind of goes on automatic. Then the next step is also automatic, because we look up behind me here, you can see that big orange arm up there. That's a robotic arm that runs on a set of railroad tracks. That'll take and come down here, pick up what we call the blank, which is all the fibers in the right orientation. And those fibers, by the way, have all the glue in there too, so it's a complete unit. Then we take and pick it up and bring it to the next station. So follow me to that next station. So this is the next station. We have a tray that comes out. The robotic arm takes and puts the part or the blank on that tray, goes in, gets heated up to the right temperature, then it comes out. The robotic arm picks it up again and then puts it in this big press that'll take and actually press the part between the two opposing halves of the mold to take and make one of the correct shape, or part of the correct shape. So then we've got another robotic arm then that's actually not set up right now, but can take the completed part off the end of the production line. So when we look at something like this is a really sophisticated process. And there's one particular one of our majors that's really well suited for this kind of a production type of process. That's mechanical engineering technology. If I was to contrast what mechanical engineers do versus mechanical engineering technology graduates do, mechanical engineers design the next generation of materials, machines, jet engines, what have you. mechanical engineering technology then takes that design and tries to figure out, okay, how do we make these? And this is a production process. So when you think about, you're really interested in how do you make things, mechanical engineering technology is a great, great major, and we've got great strength in that program. So with that, we're going to now go into the next lab here. And I will give a caution as we go into this lab. They are working on some proprietary projects here, so there's a limit to what direction we can have the camera point here. So I'm actually going to get Chris, who's running the camera here, to go in front of me and kind of look backwards at me as we kind of enter the lab. Okay, here we go. So now we're going to head into the lab and work our way down toward the side here, and we'll get to a position where we can show you not the project we're working on, but we can show you what makes all the good stuff happen. Okay, so we can kind of get Chris pointing down this way here. There we go. So this is a wind wave tank. We can generate waves on a scale basis, the equivalent of 100-foot high waves. Now when I say a scale basis, so we're working with a scaled down structure, okay? But on a scale basis, we can do 100-foot waves, and real height, that's about a 2-foot high wave. These series of paddles here are what actually causes or makes the waves. What they do is they rock forward, rock back, rock forward, rock back, and that creates the waves. And what we do is we study the effect of waves on floating structures. They could be anchored. It could be a ship model that we're towing through the tank. But we're here not studying waves. We make the wave that we want. We're studying the effect of the waves on the structure. And that, it could be a mechanical engineer doing that work. It could be a civil engineer doing that work. But those are the two majors most involved in this type of work. And then if we go down just a little bit further and kind of look back up here just a little bit, this is our this is our wind generator. So not only do we test with waves, we test with wind at the same time. We can do wind that's 200 miles per hour on a scale basis. So 100-foot waves, 200 mile per hour wind, this is the real thing. And again, this theme is that engineers need to have the ability to design, to predict, but you got to be able to measure. And facilities like this is where you actually get to measure. Another feature of this facility is we also can do tow structures through there, or so a ship, for example, ship model, and that you don't actually have the model propel itself through the tank. You actually use a tow rail to take and tow it through. And then also in some configurations we can vary the depth of water. So we got wind, waves, moving, variable depth, unique facility in the world here at the University of Maine. So a lot of facilities for our students to take and work with. So let's look at one more thing before we actually head out here. This gives you a sense of what one of these scale models looks like. This is a floating offshore wind turbine. It has 3 flotation chambers around the perimeter, 1 flotation chamber in the center. It's got the tower. It's got the blades. The blades, these are all to scale. It has a little scaled down generator up there, so it generates electricity, just like a real wind turbine floating out in the water. And this is the size that we test here in the lab. To give a sense of scale, that's a person. So I'm going to take and put the person back out on our wind turbine. There we go. So this is the real thing is quite large. We have students who do all work on projects like this at the University of Maine. We at the University of Maine have a very, very hands-on program where you really get to experience real engineering. So now we're going to take and start to work our way back up toward the front. And I should have added as we were working, if you've got questions, you can take and type those in the, what is it, the chat function at the bottom or something like that? The comment section, and we'll do our best to answer questions. Okay. Open door slowly. You don't want to wipe out the person on the other side of the door. Okay. So I'm going back out into the big part of the lab here, where we got the 3D printer. We've got more test rings with loading ramps that we can take and use to take and do additional tests. There's like some concrete panels off of bridge decks we're getting ready to test. Okay. So those are just some pictures of some of our floating offshore wind work here. You can see the blade flopping up and down. We're doing fatigue test on a blade. In the upper center panel, you can see an aerial view of our 1/8 scale floating offshore wind platform being towed into place. And in the upper left, you can see the platform being subjected to some pretty big waves. That's just that particular video is just getting ready to restart now. But anyway, these are projects that we've got going on here, and so really cool things happening. We're getting ready to go up at full scale. We should be in construction at full scale about a year from now. Just in time for you folks to be starting at the University of Maine. Going past our bridge and backpack we looked at. All right. Now at the point where I can take off this hard hat and that pair of safety glasses and put those where they live, which is right here. Okay. All right. Okay. I'm actually going to get ready and switch to my other hard hat. So here's my, got to make it a little bit bigger. So get my other hard hat. Next we're going on to our construction site. So we need to have on orange safety vest. So I'm going to get my safety vest on here. All right, and then switch to my other pair of safety glasses. Yeah, we're looking at pictures of the students who work here, as well as some of the faculty. So lots and lots of folks work at this lab. Lots of opportunities. Okay. All right, so now I'm equipped to go into the next spot here. So we're going to head outside. There. And our next place is we're actually going onto the construction site of the Furlan Engineering Education and Design Center. We stop there at the end of every tour because it's a very active site, so every time we go, there's something new that's in place. You can see it's a nice, beautiful day here in Maine. And falls in Maine are usually just some of the most incredible times of year. Even though we clearly have COVID-19, as evidenced by me wearing my face mask and stuff, we've got students actively here on campus. taking classes, doing labs, living in the dorms, all in a very, very safe manner. Just some of the things we're walking by. This is Jeunesse Hall coming up. This is where the chemical and biomedical engineers hang out. On a future tour date, that will be the focus of our tour. So come back. Remember, every 2 weeks we're doing a tour like this with a different route every week. Now we're going to cross the street. Want to make sure, especially live on the internet, that we don't get run over. That'd be very, very bad. So we don't want that to happen. You might also see in some of the background shots here that it's fall in Maine. So we're getting the leaves on the trees are starting to turn. Very, very beautiful this time of year. Other things I'll say about our program is that we have a great placement rate for our graduates. We have a 99% placement rate within 6 months of graduation. So pretty much if you want a job, you've got a job. Every October we do an engineering job fair, so that's specifically for engineering. And last year we had somewhere around 170, 180 companies that came to the job fair. And as we come up to this next corner here, I'm going to pause for just a moment because as we look up the hill here, that is the Hilltop Dormitory Complex. So as a first-year student, that's basically where you'd stay. The other side of this corner is where engineering starts. You can't get any better as far as the location of the dorms relative to where your engineering classes are going to be. So now we're going to kind of continue along. We also have lots of opportunities for our graduates, or students actually, to have internships. We have at least 80% of our students have at least one significant internship opportunity so while they're a student here at the University of Maine. And again, the way that you get that is the engineering job fair. Lots of opportunities. In addition to tours like this, we also do Q&A sessions both in the evenings and late afternoons on Thursday. So pay attention to those, and we will also and it's another great way to kind of learn more about engineering at the University of Maine. Just a general comment about engineering is that we're in a period of time in our country where there are not enough engineers. And the fact that you're watching this video or this tour and thinking about engineering as a career is awesome. So we got to step out around this barricade, and I'm paying very close attention to traffic because we're getting and now we're getting ready to go on to the construction site. Okay, looks like we're still good. All right. So we've got our hard hats on, safety vest, safety glasses. I've got steel-toed shoes on. So now we're ready to head on to the construction site. When you're on a construction site, you always want to be very aware of what's happening around you, and don't assume that the equipment operators actually can see you from their cab. So you want to be very aware of what's happening. Okay, and here we go. We got a truck coming right up behind us. Let's figure out where he's going. Okay. Yeah. Okay, so let's keep on heading down this way. All right, so now we're on the Furlan Engineering Education and Design Center construction site. This is a $78 million building, about 108,000 square feet. Let me tell you what's in this building. So first floor of this building, we have our student project design suite. It has 48 workbenches that will be assigned to a group of students for a semester or a year. That's your space. Lockable storage underneath, so you keep your stuff there. You've got your bench space that you can use, and the bench area is surrounded by shops where you actually fabricate components. So we've got a shop for biomedical engineering, a shop for electronics, 3D printing, a tool crib, a vehicle shop, a metal shop, a wood shop, and a composite shop. So the idea is you go out to the appropriate shop and fabricate components, go back to your bench and put them together. That's where you're going to take out your bench and debug your components to actually get the thing to actually work. So that's going to be the best space of its kind in the Northeast. The other things on the first floor, we have our student commons, where we have food service available, lots of comfortable seating, so you can take, and that's going to be the gathering place for all engineering undergraduates. So no matter what your major is, you're going to be in this building at least once a day. We've got classrooms in the building. These are all collaborative classrooms that are available for students to so you can actually learn in small group settings. So we've got those on every floor of the building. We also have meeting rooms for students. We have 12 of these scattered through different floors of the building. Mechanical engineering technology, remember that's the major that's really figuring out how to make things. Their key laboratories are going to be also on the first floor. The second floor is mostly mechanical engineering. So we have mechanical engineering teaching labs, and that's where we also have our mechanical engineering faculty will have their offices there. We go up to the third floor. That's where biomedical engineering is going to be. So the biomedical faculty are going to be there, as well as our biomedical teaching labs. And about half the third floor is our biomedical research labs. And a lot of our biomedical engineering students do get actively involved in research projects. So lots of opportunities there. This building is under construction right now. It will be completed in the summer of 2022, so open for classes in fall of 2022. I'm going to step off to the side a little bit, so maybe we can just kind of get some shots about different things that are happening here. What's happening on the site today is 2 days ago they poured that section of wall. The crew is taking and stripping off the forms. So they've already got the crane attached to that section there. They're getting ready to start to pull that loose. Then they're going to take and get it reset up for the next section of wall pour. If we take a look across the way here, what they're doing now is they've got the rebar in place here, and what they're going to be doing is literally flying the forms from where they are here over to the next pour, which I think is going to be diagonally opposite where we're standing. The area that you're looking at kind of enclosed here, this is just the mechanical basement for the building. It's not publicly accessible space. This is just where some of the wet mechanicals, so steam and such like that, are going to be. And the footprint of the building, this is only about 1/8 of the footprint of the building. The building actually goes all the way down to the red fence down there, and then almost up to the street where we started. So that's just a quick look-see at our construction site. The tour that is 4 weeks from today is going to really feature this site and including many UMaine engineering graduates who are key to actually building this project. So with that, thank you so much for joining this tour. Remember, we've got tours every other week. We also have Q&A sessions. Would love to have you as students at the University of Maine. Remember, my name is Dana. If you got any questions, just reach out to me. I'd be happy to answer your questions. So thank you.